Okay, guys, in this video lesson, we're going to take what we've been talking about for one-dimensional motion and then apply it to a very specific type of one-dimensional motion, which we call free-fall motion. So we'll start off with this little video clip for you.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
All right, so kind of an interesting old video, but the concept of how do things fall when gravity is pulling on them is kind of the focus here as we kind of move forward in terms of free fall motion. We'll be spending a lot of time on that, not only in just the movement and the kinesthetics of it, but also the dynamics of it, of basically why it happens later on in the year. So first thing we want to talk about is this idea that as an object falls, okay, it does so because of the acceleration due to gravity. Okay, we label the acceleration due to gravity as little g. Little g is not gravity itself. Little g is not a force. It's the acceleration that results from gravitational pull on objects. Now, g is constant for us. As long as we stay close to the surface of the planet, which we're going to for now, we can say that g is always the same value. The beauty of that is, in any of our equations, we can replace a with g for free fall. So if something is falling, or if something is launched up in the air vertically, comes to a peak and then falls back down, that's still free fall, okay? So in either case, we can replace a with g, and g is negative 9.81 meters per second squared. So if you notice, it is an acceleration. It is going to be tagged as negative because we're looking at moving downwards, okay? In free fall motion, we're going to designate direction for you, so you don't need to worry about doing that yourselves, okay? So for us, anytime we move up, we're going to call that positive. Anytime we move down, we're going to call that negative, all right? So in that case, since gravitational pull creates the acceleration, g, of negative 9.8 meters per second squared, that's in a downward motion because gravity pulls everything down, okay? We're going to set y the point that we start, okay? The reason why we do this because that allows us to kind of acknowledge where is the beginning point of our stuff, okay? So if you start by holding something at the Leaning Tower of Pisa here and you drop it off the top of that, one, you'd be arrested for going up in there because you're not allowed to. But two, you would drop something off there and it would fall and it would hit over here. We call this the 0 point, and our way down, you have a negative displacement also, okay? So for now, in your notes, make sure you're identifying that anytime we do free fall, we can rearrange this to be g versus a. Speaking of that, we really have nothing new in terms of our equations because the same math applies to free fall as it does to any other type of one-dimensional motion. All we need to do is modify our equations a little bit. So instead of having a, we're going to insert g into those instead. We're going to start tagging the subscript y to designate vertical motion. So we're going to use a little y in places that we didn't before. The reason why we do that is because in our next unit, we talk about two-dimensional motion, and we're actually going to have to track movement left and right as it's going up and down. So we're actually going to add a layer to this where we have both vertical and horizontal motion at the same time. By tagging things y for vertical, we always know which component we're talking about in that regard. Bonus for us, g is always negative 9.81. So there's no more determining, well, what is the acceleration here? What is the acceleration? If we're talking free fall, the acceleration is always a negative 9.81 meters per second squared. Okay. Now, free fall would not be things rolling down ramps. Free fall would not be things like bottle rockets flying in the air or jet planes flying across the sky. Free fall would be something that is, once you launch it, once it's in the air, the only thing affecting it is the pull of gravity anymore. That's things that are on free fall. Okay. So here's our equivalents. We have our 4 formulas that we've been using, delta x equals 1/2 and so forth. Notice the vertical formula, we just rewrite it saying delta y now. So we're working the vertical component. And we have velocity in the y direction initial, velocity in the y direction final. That's the only change. Down here, velocity in the y direction final, velocity in the y direction initial. Instead of a, we have g, because the acceleration is going to be because of gravity. Same thing down here. Notice how a is replaced with g, and so forth and so on. Knowing this, now we can do any problem that we have using the same math, the same formulas, but we just deal with it in the y direction. And we know the accelerations. All right, guys, that is it for the actual video lesson on what that means for free fall. We will have practice problems for you guys, definitely to work on to wrap up this concept, to be able to test your ability to solve this stuff now in free fall. Thank you.